Okay, am I on the screen? Can you hear me?
I can hear you.
Yep.
Okay. When last we left off, we were talking about sequencing with Arduinos and how an Arduino basically gave you the ability to have some number of switches depending on the model that you used. One of the things I wanted to add to the last presentation is that I typically start out putting sketches together with an Arduino Uno simply because it's a little bit bigger, it's a little easier to make changes to, I can add things to it. But then invariably, when I want to go and actually model something, I'll switch to this thing called a Pro Mini. And the basic reason is it's much smaller and it's cheap. I've seen these actually offered for $1.65 a piece. And they range all over the map up to about $8. I usually buy them in quantity 10. I usually get mine from China, and 224 is, I think, the last price I paid. So the reason for using each one of these varies, but I typically will start with either the Uno or the Mega down here, and I'll migrate to the Mini. The thing that I had to get in my mind is that the Pro Mini is about $2 a piece. I had to start thinking about it as a component, as another tool, because the substitutions invariably ran into more money, cost me more time, cost me more space, and kept pushing me back to using the small, as effective unit as the other one. So that's just a comment from the last time. This is going to be the last in this current series on animation talks. I need to take a hiatus to deal with other demands on my time. And I thought we would actually leave off with the start of talking about animation with movement. And of course, this is one of the characteristics of looking at something and you sensing that it's alive. We talked about all of these different kinds of movements the last time. And in considering guided and steered, you have to realize that there's something that's actually going to steer them or guide the movement. And we do that with sensors. Sensors are another kind of switch, and they can also feed into an Arduino and be detected. The last thing in the sequence that I didn't touch upon very much before is that an Arduino can actually do something that you can't get with other kinds of mechanical switches for the most part. And that is that you can actually generate a random number and create a random effect. Now, it's not truly random by mathematical standards, but it will give you the impression that the sequence is just jumping all over the place. For example, in the building lighting that I demonstrated at least once or twice, if you actually were to calculate when that pattern for the entire building set of lights would repeat, it comes out to something like 1.37 years. So no one is going to stand at your layout trying to look for a repeat in the pattern. But you can certainly get to things where you could easily determine the pattern, and those tend to be boring. To generate movement, you're going to use different kinds of motors. The big issue with animation and movement is getting things to run slow and smooth, no jerky motion, regardless of the scale that you're operating in. And typically you're looking for very small motors. My friend says that I have the largest collection of motors, particularly small ones that he's ever seen. I've been collecting small motors that are particularly geared for over 20 years. And I typically will go and look for something that's less than $2 a throw. And a lot of the motors I'm going to talk about today, you could have obtained at one point or other for less than $2 a throw. I'm also going to wind up today by talking about servos. And a servo is a very special kind of motor that it turns out you're able to control and direct trivially with an Arduino. And that's going to become a really important thing, and we'll try and get to that. These are from my collection of motors. You could get motors with a right-hand drive that are geared. The N20 refers to the actual size of the motor here. The N10 is about half the length of this motor up here. There are very tiny motors. If you have a cell phone, sometimes it vibrates. These are the motors that actually generate the vibration. It's a tiny 4x8 millimeter motor. And on the end of it, there's an off-center weight. And as it rotates very, very quickly, these things tend to have like 12,000 RPM associated with them. When you weight it down, they don't go that fast, but they will generate the vibration. And that's why the off-center weight. It turns out if you look closely here, you can't really see how that weight is attached. Well, originally it starts out fitting very easily on the shaft, which is about 0.6 millimeters. And then if you look really closely, you'll find a dimple right there. And that's where they hammer it and lock down the weight on the shaft. If you see a weight attached like that, it's almost impossible to get off without damaging the shaft and therefore the motor inside. So if you go after little tiny motors like these, and I'll give you an example of how I use them, you really should look for them without the weight attached. You can find them like that. These are great motors down here. These are 8 millimeters across here, cylinder, but they've got a planetary gear head over here. Planetary gear has a gear right in the middle, surrounded by usually 3 gears, and they're stacked one on top of the other. This has more stacked up and therefore goes slower at the shaft on the output. And you'll, actually, I have this reversed. This is the 36 millimeter, the 36 RPM motor, and this is the 1200 RPM motor. So they're backwards. More gears means you have more gear down, means that it's going to actually turn the end shaft slower. So that's what's going on there. Here, one of the very simplest examples of an animation with movement, a simple sign that you can turn around. It's got a collar down here. It's got a shaft that goes all the way up, and that shaft is directly connected to one of the geared motors. The collar over here, it turns out, is fundamental to making this thing work, because if you didn't have that, this thing will tilt and wobble all over the place. So this is a telescoping tube right here. And by using that telescoping tube anchored into the base, you don't get any wobble, and it really comes out working pretty well. Here we have a pretty simple kind of animation, very simple design, no Arduinos or anything else, just like the rotating sign. It's got a screw shaft over here going back and forth with a magnetic clutch. So there's a pair of magnets under here and a pair of magnets underneath the forklift. And it's pulling the forklift back and forth. And when it gets to the far end, it'll trip that little tiny micro switch there and a little tiny micro switch at the other end. And that is going to activate a locking relay, a latching relay, and that will simply make it go back and forth. And that's all it does. You can control the speed by controlling the speed of the motor over here, and that is a geared head motor on the end as well. But the real drive down on the gearing is actually the shaft. That's a 440 screw, no, that's a 256 screw that's attached directly to the axle of the motor, and it's just driving this back and forth. So it's pretty easy to do. I mentioned before what you could use those very tiny motors. Remember, this is only 4 millimeters across by about either 6 or 8 millimeters long. And I use this as a stall motor, the same kind of stall motor that you would see throwing a switch, except this is really tiny. And the critical issue with a stall motor is some motor that when you stall it out is not going to draw a lot of current and it's not going to heat up. So this is absolutely critical to this. And all this does is activate for 1/2 of a turn. So literally you're driving it forward and it will turn 1/2 turn. You drive it back and it turns 1/2 turn the other way and stalls in each way. What is it for? To reverse the head of the engineer that we're about to see. That guy has been reworked from an old plastic bill figure of a reverend. You can see the steps to rework it. Excise his head, put a shaft there, and away you go. And here's where we'll see it. Oh, sorry. Push the wrong button. Let's try again. There we go. Now watch the engineer. He's always going to face the direction that the easel is going to go. This is an HO model, by the way. And here we go reverse. There he goes. And he'll go back and forth like that. It's a really interesting little tiny animation that'll catch people's eye when they're least expecting and generate some interesting comments on your layout. Here we have another very simple animation. This uses a belt drive. This is actually an elastic band, elastic stretchy cord that's used for beading. The reason it's used is simply because you can't get a motor and its drive close enough here, because this is an HO scale, fully animated barber pole. It's not like the ones that they sell, which are actually closer to O scale, and they claim you can use it. Well, if you use it, you know, it's twice as large as it needs to be. The little globe at the top is another bead that you place an LED into. We talked all about LEDs, and here's the side mechanism here. And that's all it is. And you can get an idea of how it operates. So the barber pole turns, the light lights, and that's the little animation. The inside is actually a picture that's placed there of a barber shop. Bob's Barber sign is also backlit, akin to Harry's TV sign that we talked about once before. Here's another animation, again, very simple movement. This is a band drive. This is a simple elastic that you can get at a store like Michael's, and it's butt glued together around a motor-driven capstan. Here's the motor up here, driving this capstan down here, and this is just a pulley on the other end. This is a modified figure that we're going to place inside of a coach, and he's going to become the ticket taker. And I showed you a very short snippet of this before. Now, in this one, it's kind of an oddball because I'm actually using a decoder that's nothing but a lighting decoder, and it turns on an Arduino that does the animation. And in this case, you're starting and stopping the conductor doing his ticket taking randomly along the way. So there's an example of introducing randomness in the animation. Oop, did it again. Okay. Okay, here's another one where, again, there's no Arduino involved. It's a simple motor drive with that planetary drive motor that I showed you before. In this case, that motor is right here, and it's driving an offset cam that's going to raise and lower this arm over here. And that is actuating this little tiny pin like you would have for a track switch. And it's going to raise and lower the arm here of the blacksmith. But at the same time, it's going to actuate a switch over here, a little tiny micro switch. And that is going to trigger a little tiny audio player over here. And this is the result you get. So you get a very nice little blacksmith animation. No Arduino involved, very simple trigger, which is just a switch. And those switches, in fact, are the key to a lot of this. And Arduinos, you remembered, can't drive a lot of current. But if you want to drive a large incandescent lamp, or you want to drive something that's going to take a lot of current, you can take that pin and amplify it with a very cheap transistor and drive a solenoid, a lamp, a motor, or any other kind of higher power device with very little expense. The resistor and the transistor would probably cost you 60 cents, if that. There are more sophisticated things you can do from an Arduino pin. You can directly drive a relay, and that relay can act like this switch over here, except that now you can have a relay that's latching. You can have a relay that's 4-pole double throw. You can make it do all kinds of interesting things. And there's the DigiKey catalog numbers for that. You can also run an animation with animation motor with a dual H bridge. And eventually we'll get to talk about that in the next series, the follow-on series. You can also use a DCC decoder in conjunction with an Arduino to drive things, and that generates some interesting things too. Last for this time, I wanted to touch on servos. A servo motor is not just a free running motor. A servo motor actually needs a very particular kind of signal to drive it. And the typical servo will go a half a turn. Now, they're typically talking about a quality servo will go from 0 to 180 degrees. It turns out the really El Cheapo servos will go from about 10 degrees to about 170 degrees. And these are the ones that'll cost you like $1.69. Those are typically 9G, 9-gram servos. They look a little bit like this, but they also come in smaller versions. This is a 3G servo. That's pretty small. There's also a 4.7G servo. That's sort of a little bit halfway. The way you drive that is you have to feed it an electronic pulse train, a set of pulses repeating over and over again. And this is critical. If there's no pulses there, the servo doesn't know what to do. But if the pulses are there and they're well formed, then the width of the pulse determines where in the arc it's going to position itself. So you start with a width about 1 millisecond wide. It'll position at the 0 degree end. 1.5 milliseconds wide, you position it at 90. And 2 milliseconds wide, it'll go to 180. Now, these are approximations, by the way. You also provide it with 4.5 to 6 volts DC. So you power it, but you need this signal. Now, it just so happens that the Arduino can generate that signal trivially. And even the little one that I showed you before can generate 18 of those signals simultaneously to control 18 servos. So that's an advantage of it. You can also control one. So that $2 module, that $2 component I was trying to emphasize before, can actually control these. Now, with servo control, there's a couple of things you want. You want to know the accuracy of the position. And the second thing is you want to maintain it sometimes. If you want that position held, then it has to be powered. If you let go of the power, it might joggle back and forth one way or the other. The other neat thing about it is you can attach these things called horns, and they go up here. You can see one attached over here, and they are the things that turn. So you provide leverage by providing short and long horns, one-sided, four-sided, etc. You can also get a little tiny thing called a blade servo, and this goes back and forth. They simply take that power, and using a similar method, they're going to position it from one end to the other. And that's only about roughly 1/2 of an inch. But it's really neat because then you get linear motion that way. I was talking with Jim before this started, and he was interested in raising and lowering a pantograph or a trolley pole. This is the kind of servo we were talking about before. You can power them and control them, and control is the big issue. There are commercial units that you can use, or you can use Arduinos. And here are a couple of different examples. Here's a button control to move the servos that are documented in that article that I cited last time, introduction, a modeler's introduction to Arduinos. And there's another one that I think is also in that group of references. And this is DCC multifunction decoder control. This is actually using an Arduino as a DCC decoder that can drive 17 servos independently. And you can do that with either an accessory set of switches, or you can do that with 17 functions on a mobile decoder. Here's an example using servos just to control doors. Now, obviously, here's a cargo door sliding back and forth. You'll also see the figure approaching the door and being taken away from the door after it opens. This is all being done simply by this Arduino that's running over here. Here's a door that just is going to pivot. Typical door opening. We could use it on our gray house, in fact. And I want to show you behind the scenes what's actually going on to give you an idea of how those servos are actually operating. So here's the servo that's opening the door. Here's the servo that's moving the figure. And here's that little tiny blade servo that's opening the side door. And notice they all have a linkage to the door. This one's got a very straightforward linkage, and all it's doing is moving it back and forth. Here's the linkage to the sliding door over here. Very simple, very straightforward. The linkage to move the figure is actually very direct off of the horn of this servo over here. So you can use these servos to get all kinds of interesting, slow, controlled motion. I mentioned a couple of things before: modeler's introduction to the Arduino up top. DCC projects using the Arduino will show you how to create that DCC decoder that, in fact, will go and control those 17 servos. So I hope you enjoyed this introduction to animation with movement. When we resume in the next series, Jim has been kind enough to ask me back. We'll be talking about more kinds of control for movement with Arduinos and sequencing for animation. But we're also going to talk about sound and synchronizing the sound with movement, synchronizing sound with light, and that'll make for even more interesting kinds of animations. Are there any questions?
Geoff, on the sliding door on towards the end of the presentation, there was a horizontal sliding door.
Yep.
The lever that moved that back and forth had a bend in it.
Yeah.
Was that for fine adjustment?
Yeah. That's because you can be sloppy if you have that bend in it. Think about it as a linkage for a switch machine throw. If you got that bend in it and you're a little bit off, that bend will take up the slack. So it won't push too far, it won't jam anything, and it works really great. And that's why the bend is there.
I kind of like an omega spring, sir.
You got it.
Thank you.
Any other questions?
Geoff?
Yo.
If you can send me that last slide with all the stuff in it, the links, I can put that in the chat if you can send me the a text file, or just send me the slide so I can cut and paste.
Let's see. What I'll do is
modeling@gmail.com.
Well, what I'll do is I'll put in the chat a link to download the entire slide set.
Oh, that works too.
As a PDF, okay?
That'll work for everybody.
Okay, very good. I'll do that.
Geoff, thank you so very much. This has been just fascinating stuff. The whole series has. And I